Okay, question 4M7 from Statistical Rethinking. Before you run any of this code for yourself, make sure that you have the Rethinking package installed and you've loaded the Rethinking package with these codes up here, or bits of code here. Okay, so what it wants us to do is to modify a model that was presented earlier in the chapter, model M4.3. Okay? And the way that we're going to modify it, so here is model M4.3, and we're using a data set that's available in the Rethinking package called Howl, and we're just using individuals over 18. And we are modeling the height of these individuals as a normal distribution, where the mean of that normal distribution is being modeled as a linear model with a intercept and then a beta term or a slope term that is contingent on weight. So in other words, we're modeling height where the average height is some function of weight, right? So that makes sense. We should be able to predict height somewhat by body weight. Okay, that doesn't mean that weight causes height or anything like that, but that's neither here nor there. We're just predicting in this case. And the way that the question wants us to change this model is with this term right here. So the original model centers the weight variable on its average, which we called xbar. Xbar is just the average of the weight. Okay, so it wants us to do the same model but without this centering, so just beta times weight, which is what we've done in our model here. Otherwise, they are identical. Okay, so we're going to compare these models in a few different ways. And so the first way that we'll do it is we will just look at the posterior distributions for the parameters. Okay, so we're running that here. So the Prezi function is just a summary function in the Rethinking package that kind of presents a nice clean output. So the top data frame here is the original model. So here, this is the original model. And then we have the the new model. And so let's compare these. So let's look at the sigma value first. And so these are basically identical between the two models. And the beta term, which is, again, the relationship between weight and height, these are very similar, not identical, but that's fine. They're very, very similar. Finally, the intercept term. Now, the intercept terms are noticeably different from 114 to 154, 155 in the old model. So what could account for this? Well, we know that it probably has to do something with the centering effect. Okay, so what accounts for this is, so the intercept term, this alpha term or the A term here, the parameter A, that is the value of mu when this product is 0. Okay? Now in the original model, mu equals A when this term equals model, or when this term equals 0. Okay? Well, so in other words, this term equals 0 when weight equals the average weight, but here this term equals 0 when weight equals 0. Okay, so in other words, alpha is being pushed around by the product with B. Okay, so that's what's happening there. The other thing that the question wants us to do is to examine the covariance among the parameters. So the covariance among A and B, and A and sigma, and B and sigma. And so that's what we'll do here. But rather than looking at the covariance, which we could do, the variance covariance among all of these, we're going to convert it to a correlation just because it's a little bit more natural to look at. So I'm going to put out these correlation tables among the parameters, and then I'm also going to plot it with the pairs command. You'll notice that there's this suppress warnings here. It gives an annoying warning. I'm not sure why, and I didn't know how to fix it. So I'm just doing that just to make the readout cleaner. But the important command is the pairs command here. Okay. All right. So let's scroll. Okay. So this is the old model. This is the covariance or the correlation matrix for the old model versus the new model. Okay, and so in the old model, we see that there is basically the parameters are always perfectly correlated with themselves, right? Alpha is 100% correlated with beta, so on, okay? Or 100% correlated with itself, beta is completely correlated with itself, and sigma is. This is just by definition. And we see the same thing in our modified model, 100% correlation between the two. But what is different is that there are all the other correlations among the parameters in the first model, they are 0, but not for the modified model. So we'll take the correlations with sigma to be 0. They're basically 0. We'll just take them to be 0 in this case. But there is a really, really strong negative correlation between the alpha and the beta parameters. Okay, and so if we plot these, you can see this in the plots. Okay, so in the pairs plot. So if we just have, so here's the posterior for alpha and beta in model 1, and these are those, if we were to plot in alpha and beta space, this is what we would get, and you see there's really no correlation there. But in the modified model, there is a very strong negative correlation between the alpha and the beta parameters. Okay, so what's happening here? Why is there this negative correlation? So this takes a little bit of thinking, and I'm actually not entirely sure that I have it completely right in my head, but it is something like this. Okay, so the first thing is to explain what this correlation is not about. Okay, what this correlation is not. This correlation is not really capturing a relationship between height and weight, and I feel like that's a very your mind almost wants to make that connection, that somehow there's some connection between height and weight. But that's not what's going on here. And even if the correlation that does exist is not negative, it would be positive. Okay, so what's going on here is something like when, let's say that beta is low. Okay, so let's say that we have a low value for beta right here. Okay, so if there's a low value for beta, in other words, the relationship between height and weight is weak. Well, if the relationship between height and weight is really, really weak, well then there's a lot of the average height that has to still be explained, and so all of that gets shifted over to A, right? So when we guess a low, so when the model is guessing a low value for B, which would be over here, it has to guess a high value for A, okay? And vice versa. If it's guessing a strong relationship between height and weight, where beta is very big, well, then there is less of the average height that needs to be explained by A. Okay, so now that effect should actually be present in both models, but because in the first model, the thing that beta is multiplying is much smaller, it's smaller by xbar, or xbar has been subtracted from it, then that push and pull between alpha and beta is much reduced. Okay. Let's see. Okay, and the last thing that it wants us to do is to compare the predictions of the two models. Actually, we don't need those commands. I guess I'll keep them though, just because. So this code, maybe we'll walk through it really quickly here. So here I'm setting up a sequence of numbers that is just a weight sequence. Okay, so it just puts a sequence from the minimum weight that we found in the data to the maximum, and it just marches steps out until it starts at the lowest value that we found for weight, and then just marches up to the highest value of weight, and it gives us a certain number of them, and they're all evenly incremented, and that's going to help serve as an x-axis when we start plotting these things. Okay, and then I want to find the mean, or examples of the mean, for both posterior distributions for both models, one here and one here. And there's several ways to do this, but there's a convenience function in the Rethinking package called link, and that's what I'm using here. So this is, well, maybe I'll just show you what link puts out. So if I take this guy right here, give that to you. Okay, so what Link has done, go back up here, is it takes it gives us the average, or it gives us estimates of average height across the different weights, right? So as I go along this column, okay, this is one set of parameters in the posterior for alpha and beta across all of the different values for weight, okay, and it just marches across. The next, another row is just going to have a different set of alpha and beta parameters, and it just marches it across all of the different possible weights, okay. Now, similarly, we can simulate data, okay, with the sim function, okay, and we'll also be plotting this. And so what does the sim function give us? Okay, the sim function gives us something similar, but not quite the same. So again, as we march across here, this is giving us values at different height values at each of the different weights that we're looking at. Okay, and this is one set of parameter values, and this is another set of parameter values, and this is another set of parameter values from the posterior distribution. But this differs from the link function, or from the mu objects, in that this one adds in the sigma, that it adds in the variance, or the standard deviation. Okay, so this is actually trying to replicate data, whereas the mu is just trying to show you the mean at each weight value. Okay, all right, and you'll see these in just a second. So now we're going to plot these. We're going to plot these for the first model, and that will kind of have a red tint, and then for the second model with a blue tint. So let me run these. Okay, so here's the model in the book, and here's our model, and they're identical, but just to show you what is happening here. So the black dots, this is the original data, so that's identical between the two. Okay, this way we can kind of see how the predictions of our model mesh with the actual data. Okay. So the red dots are data that was generated with the sim functions here and here for the two models, right? The dark red line, or dark blue line, it's in an envelope of a kind of a lighter shadow there, but that is the average value at each weight of the mu functions. Okay, so here's the line. So I've taken so here's my mu object, and I've taken the mean at each weight. So I just get a single line, and then that envelope, that shading, is I'm using a HDPI, a high density credibility or probability interval, to show this is the credibility interval of the average. Okay, and you'll notice that it's the same for the two models. Okay, so even though the first model uses centering and the second one doesn't, they put out the same predictions. So why would we care? Why not? Should we have a preference for one over the other? Well, it may be that one of them is easier to interpret than another one. For instance, in the centering model, the intercept has more of a realistic interpretation, because again, this equals the value when weight equals the average weight, and that is a value that is probably in the data set. Whereas here, alpha has a tougher interpretation because it occurs when body weight equals 0, but body weight never equals 0. And so considerations like this kind of help determine which model might be preferable.